Swayam Prabha. Digital India. Educated India.
And now the question comes, what do we mean by the probability of a tree? And what do we mean by computation of that tree probability? What do we mean by the probability of a tree? How can a tree be probability? So then we ask a more basic question. What is the random experiment here? What is the random variable? The random variable is t given s. Okay, what is the tree given the sentence? So this random variable of what is the tree given the sentence can take multiple values. And these multiple values are not deterministic. It can take any value, any tree, and therefore there comes the question of scoring them. So first let us cement our understanding of what is the probability of a tree. How do I understand this notion and how do I compute it? So to understand that, I again go back to this example. I saw the boy with a telescope. So I get the parse tree here. Now just like
Sir,
in, yeah, hello,
sir,
yes.
how P by S, P by T given S is 1.
Yeah, because you see, if I take this
So
example, can you see that screen? Saw the boy with a telescope?
yes, sir, yes. Sir.
So now you see, if I've got this tree, my sentence becomes unique. I simply pick up the leaf nodes, okay, left to right. I saw a boy with a telescope. So given the parse tree, the sentence is unique. Is it okay? You cannot get two sentences from a parse tree. You can get two trees from a sentence, but never two sentences from a tree. Do you get it? The person who asked the question?
Okay, sir.
Okay.
So in
Yeah.
this, the parse tree, when we say parse tree, should we
Mhm.
say the means are we including the sentence also with it? Means
Yes. Yes. I mean, the parse tree is built on top of the tokens which compose the sentence. So see this, from telescope I got noun, from A I got determiner. From determiner and noun I got noun phrase. I combine these two. And then from with I got preposition. I combined with NP, P with NP and got the preposition phrase. So you see, part by part I consume tokens and get the parse tree. The sentence comes at the leaf of the tree.
okay, yes, I got it.
So given the tree, the sentence is unique and the probability of the sentence is 1. So this tree has this sentence has another parse tree where a telescope is at the same level as V and NP. Saw a boy with a telescope. So two parse trees are there and I'll calculate the probability of both the parse tree and will output that tree as my result, which has the higher probability value. Now, I saw a boy with a telescope. I saw a boy with a telescope. Both the meanings are probable. Okay, I have the telescope, or the boy has the telescope. Both are probable. But I saw the boy with a ponytail. Ponytail is a kind of hairstyle at the back of the head. Here, a ponytail is with the boy because I cannot see something with ponytail. Ponytail is not a seeing instrument. So there I would expect, I saw a boy with a telescope. I saw a boy with a ponytail. We'll have this structure, okay, this parse tree, where the NP contains the preposition phrase. The other structure is that the verb phrase contains the preposition phrase. If the verb phrase contains the preposition phrase, then I have the telescope. If the noun phrase contains the preposition phrase inside NP, then the boy has the telescope. Okay, so this is the way the structuring is done, and we have to find out the probability. Now, what do we mean by the probability? of a tree. What is random? Okay, what is random about a parse tree? So that is something we need to understand. What is random about a parse tree? So again, appeal to your understanding of part-of-speech tagging. What is random about part-of-speech tagging? Well, at every position you can have multiple part-of-speech. Okay, at every position you can have multiple part-of-speech, and therefore, there is this randomness in the situation. Here also, at every position, I can have a different subtree. Okay, so that is the randomness in the situation. So given telescope, I can have multiple part of speech. Suppose part of speech ambiguity is removed. Then given A, I got determiner, that is fine. Then determiner and noun, does it give rise to an NP? It so happens that in this case it gives rise to NP. But it could have given rise to some other phrase also. Okay, some other phrase also, or some other structure also. So that would produce an ambiguity. So at every level, there is a potential ambiguity with respect to what phrase structure can be built so far. Okay, and there are multiple options of creating that phrase structure. So that is why it is a random experiment situation, and the random variable is the phrase that we can uh, extract out of whatever has been seen so far. So this is expressed by a notion called domination. Okay, domination. So so let me just describe domination. I have skipped over a number of slides. So the notion of domination. So can you see this screen here? We have written domination there. It is probability of a parse tree. Are you seeing domination?
Yes.
You dominate. Okay. So we say Nj dominates from K to L, symbolized as WKL. Okay, symbolized as WKL. If it is derived from NKLJ. Okay, I'm sorry, the symbol has not come in the same line. So here it is. Okay, so if I have a sentence and I study the sentence from kth position to lth position, then I ask, is it derivable from a non-terminal NJKL? So lower suffix KL means from position K to position L, and J is the jth non-terminal. Okay, J is the jth non-terminal. So this is the notion of domination, which means, is there a subtree rooted at NKLJ which is spanning from kth position to lth position? So let's go back to the tree that we are observing. I saw the boy with a telescope. So here the noun phrase dominates a telescope. Preposition phrase dominates with a telescope. A noun phrase dominates a boy with a telescope. A verb phrase dominates saw a boy with a telescope. And finally, S dominates the whole sentence. Okay, the segment I is dominated by noun phrase. The segment from saw to telescope is dominated by the verb phrase. Okay, so the domination is again composed of many sub-dominations. Within a dominated territory, there are sub-territories which are dominated. So just like the capital of a country dominates the whole country, the capitals of the states dominate the whole state. The district headquarter dominates the district. Okay, so this way the region of influence goes on getting focused, and finally we have a position in the sentence which is dominated by the word, and the word is dominated by the part of speech. If I have two consecutive words, okay, then these two group of words can be dominated by a chunk, and multiple chunks can be dominated by a phrase. Okay, so this is the way domination is built out of smaller dominations. Just like the domination of an organization or the domination of a country is built out of smaller dominations. We can take the institute IIT Bombay. IIT Bombay is dominated by the administration of IIT Bombay. But the department is dominated by the department's administration. The head of the department is ruling over the department. Okay. Then within the department there are labs. So there are professor in charges of particular labs. So professor in charges rule over the labs. But this ruling is composed together to create a bigger ruling, and then a bigger ruling, then a bigger ruling, and so on. So similarly, this is the way a sentence is dominated by the symbol S through domination of segments by phrases. So please understand this particular notion, which is key to understanding parsing both linguistically and probabilistically. Okay, so the notion of probability comes into play because we are not sure what will dominate how much of segment. Okay, what will dominate how much of segment. So this actually should be converted to a slide, Jyotsna. This explanation of domination with example of countries domination and departments domination. Please give this example. And now my statement as to why probability comes into play. The question of domination, whenever it is uncertain, brings in probability. So for example, I do not know which part of the sentence is dominated by which non-terminal. Okay, to give you an example, in the earthquake, so this example should be on the slide just now. So in the earthquake, old men and women were taken to safe locations. So let me just take this sentence. Old men and women were taken to safe locations. Old men and women were taken to safe locations. Now the question is, does old modify only men, or does it modify both men and women? Okay, so an adjective phrase which is composed of adjective and noun phrase. This adjective phrase, does it dominate only old men, or does it dominate old men and women? Okay, if you look at the sentence and hear it, you can see that we cannot disambiguate this without more information. Old men and women were taken to safe locations. Who was old? Men and women both, or only men? Okay, so both are probable. Only the women and the old men were taken to safe location, or both old women and old men were taken to safe locations. So this is the example which illustrates ambiguity, uncertainty, and calls for the instrument of probability to be used in this situation. So this is an important notion, and I would like to at this point leave discussing a topic, because you have to really live with this notion of domination and why probability there. Now again, domination is a contribution from linguistics to computer science. The notion of domination came from linguistics, and computer scientists are very familiar with tree and subtree. Tree and subtree was given the terminology of domination and subdomination in linguistics. So when people understood that under a at the back of a sentence or below a sentence there is an underlying tree structure, then one could deal with the concept of domination and subdomination. So let me just end with saying that sentence dominates S dominates the whole sentence, and that domination is carried through by domination by noun phrase and verb phrase. Verb phrase is domination is through verb and more noun phrase. Noun phrase's domination can be through preposition phrase. Okay, and how much text is dominated from which position to which position, that remains uncertain because of structural ambiguity, and that's where probability comes into play. Okay, so we'll elaborate this topic further and build the whole theory of probabilistic parsing and how machine learning deals with this. Let me just go to the end of presentation and talk to you a little more about possible project topics. So last time we talked about project topics, possible project topics in poetry, its translation by maintaining the rhythm, and question answering based on poetry where there is a lot of subtle information which needs to be uncovered. Uh, uh, there can be interesting projects, useful projects on tweets. So informal text to formal text as well as translation. Humor, is the sentence humorous or not? That can be your decision. So I filed a lawsuit against the airport due to my luggage being lost, but I lost the case. So is this sentence interesting? It is, because it is not clear if I lost the luggage or I lost the lawsuit. So the more projects you can have, social network related, very interesting and useful projects. An important project, for example, is automatic population of LinkedIn profile from the home page. For example, the publications. So as a faculty member, I have publications listed on my homepage, but they are not up to date on LinkedIn, for example. So give me a module which I'll invoke, and it will pick up all the publication information and put it in the LinkedIn. Okay. Then translating Facebook posts into multiple languages. This is very important for government administrators, organizations. What are people writing about the organization or the government into Facebook? And we need to understand it in multiple languages. So that also, by the way, linked with the problem of fake news, okay, and proliferation of fake news, hate speech, and so on. Linking Instagram with Facebook, automatically captioning Instagram picture with Facebook post. So I post pictures on Instagram and I also talk about in Facebook. So integrate and synergize Instagram with Facebook. Aggregate search results from multiple social networks. So Facebook, LinkedIn, Instagram. I give a query and extract information from all these social media and give me a collated information. Information retrieval and information extraction also can give many very interesting projects, just like machine translation. So summarization is very important these days. There is so much information on the internet. So can we summarize multiple documents? And the challenge becomes many folds when multiple documents come from multiple languages. So can we also do summarization along with sentiment? We did some work in this area in 2016. This uses multitask learning and also what is called submodularity. So look at this sentence, oh no, forgot to send the letter. The essential information here is I forgot to send the letter. But there is pragmatic information. I am expressing disappointment, oh no. So summarization will discard exclamation and just say that I forgot to send the letter. But I lose valuable information, namely the sentiment that I am disappointed. So how to strike a balance between maintaining sentiment as well as giving a concise summary of the text. Tune search is becoming important in music information retrieval. I give the song, I hum the tune in front of the computer. I just hum it, and it retrieves the song name, the lyrics, the composer, movie name, and so on. So this requires feature extraction from sound, and we have a number of deep learning based tools which extract important features from the sound. Okay, so there you don't really have to break your head. The feature extraction can be done for you by a tool, and then you write a good classifier. Automatic speech recognition, natural language understanding, and text-to-text speech. This is a pipeline, and can we do this wholly or partially? So there are a number of very interesting problems which can be done using ASR, NLU, and TTS. Maybe next class I can list many of the problems. Explainability has become important. We have also done quite a lot of work. In fact, one PhD is happening on explainability, where we want to understand what is the neural network doing. So from the word embeddings, you try to interpret what these components mean. So word embedding gives you a three-dimensional vector of the word. For example, dog, cat, and tiger, you get these three vectors. Which components are indicating carnivorousness? Dog, cat, tiger, they are all carnivorous animals. So which component or which group of components is indicating carnivorousness? This is a very challenging problem, not yet solved. Can we extract rules from trained neural networks? Back in 1990, I had a PhD student who extracted rules from trained neural networks. And after that, this area was forgotten. Now it has come back again because deep neural networks are not interpretable. Can you extract rules from them and then understand what is going on? Can we shadow a neural network with decision tree or support vector machine? That means a neural network has been trained. Can we shadow it? Shadowing means go side by side. Can we shadow this with a decision tree or a support vector machine? The decision tree will give the rules and support vector machine will give the features. Okay, so these are very useful and interesting problems and absolutely live problems or topics. So I'll keep on adding such project topics in the slides. You can take a look. Okay, so now I can take questions.
Right, sir. Should we start with the yesterday's questions?
Yes, you can.
Okay. So Mohammad Ali Rihan asked, "What is the 1-2 in the top-down parsing slide?"
What is 1, 2 in the top-down parsing slide? Okay, so this one is the position of the pointer, the input scanner. So 1 means it is in the beginning of the sentence, it is yet to see, it is yet to consume any word. 2 means position number 2 for the input scanner. That means the first word, first token has been consumed.
Kaveri asked, "Is this parsing the same as RD parser of compiler?"
RD.
Yes.
RD, I have not heard of this term. So it's a recursive descent. Yeah. I mentioned it during the discussion. This is recursive descent parser, yes, RD.
Right. Kaveri also asked that S to NP VP and NP to DT N and NP to N are these standard rules?
These are fairly standard rules, but we have
Okay.
not shown all possible rules of NP. Yeah.
Mohammad Ali Rihan also asked, "How did we get the last S for the whole sentence?"
Last S for the whole. We did not in top-down parsing or bottom-up.
That's not written in the question. Rihan, can you please elaborate?
Bottom up parsing.
Bottom. Okay. Bottom-up parsing. So from people I get noun and verb. From noun and verb I get noun phrase, verb phrase, and from noun phrase, verb phrase I get the sentence S. So so I go on going from right hand side of the rule to the left hand side. That's how I get the S.
Okay. Sarvesh asked, "The CYK algorithm would result in ambiguity, right? If a word can have multiple tags, building can have both noun and verb tag. How did we fix a noun instead of verb?"
Yeah. So this I said parsing comes at the fourth level. After morphology, part of speech tagging, chunking, then comes parsing. So by that time, it is assumed that the part of speech tagging is correctly done. If the part of speech tagging is wrong, then parsing also will be wrong. So
Uh,
building can have multiple tags, but here after part of speech tagging, it has only one tag.
Parth also asked, "How was 2 to 7 VP?"
2 to 7, sprayed the building with bullets. Yeah, this was asked by somebody else also. So VBD NP, so VP can be composed out of VBD and NP. So here you see sprayed is VBD and the whole sequence of words, the building with bullets is an NP. It is an NP because DT, the building is NP, with bullets is PP, and you can see there is a rule. NP can be NP followed by PP. That is why.
Right. Let's move on to today's doubt, sir.
Yeah.
So there is one doubt which you have already answered during the lecture, and the next one is by Saurav. So P of t given S is the same as P of t just by definition?
No, not by definition, because the likelihood probability became 1. Okay, the
Sir,
likelihood probability became 1.
you mentioned that the T itself contains S sentence as a part of it.
You're right.
So what's the meaning of T given some S?
Probability T given S. You are asking about the expression PT given S.
Yeah, so T already contains one S. So if this S is different, then it's zero. Otherwise, it's one. So is this the only one?
Oh, no. So look at it from random variable. So the random variable takes the value, multiple values, and these values are different parse trees. So given the sentence, I saw the boy with a telescope, it has T1, T2, T3, and so on. So each of them has different probability values. So given the sentence, the parse tree is not unique,
Oh, right. Got it. Okay.
but given
Thank you.
the tree, parse sentence is unique.
Moving on to Rishi's doubt.
Hmm.
P of S is equal to S given T can be equal to 0 for some trees, right?
Come again?
P of S is equal to S given T can
Hmm.
be equal to 0 for some trees, right?
Probability of a tree given sentence equal to 0. Okay. It can be. I mean, given the sentence, I saw the boy with a telescope. If you have a tree which is coming from the sentence, Delhi is the capital of India, then that probability will be 0. So probability of a given a sentence, any tree in the whole universe is probable. Okay, except that most trees will have probability 0. Why will it be
Rishi,
zero? Why will it be zero? That is interesting. Why will it be zero? No, I am answering. It will be zero because some term in the whole product will be zero. So probability of this sentence, I saw the boy with a telescope. Probability of Delhi, given something in the sentence, will be zero because Delhi doesn't appear in this sentence.
Okay,
okay,
sir. Thank you.
the last doubt by Shreya Pathak.
Hmm.
So a non-terminal dominates all the nodes in this in its subtree.
Yes, yes, yes. That is correct.
Okay, I think in that case we are done with the doubts, sir.
Okay.